Hello everyone, this is the continuation video on solid state. This is solid state part 17, and in this video I'm going to discuss the two important ionic solids. One is fluorite, another one is antifluorite. In the previous videos we discussed two different ionic solids. One is rock salt, another one is a zinc blend. But in this video two structures I'm going to discuss. One is the fluorite, another one is antifluorite. But the same thing as in the case of previous videos, whatever the sequence we followed, here also we are going to follow the same sequence. First we need to remember the location of cation and anion, like which ion is forming the lattice, which ion is occupying the voids. If you can remember that information, the remaining things can be developed spontaneously. So without remembering so much unnecessary stuff, so we can easily derive whatever the requirement we have in the examination, right? So in this, so here calcium plus 2. So first thing is a fluoride structure. So fluoride structure, that is a CaF2. But in case of this fluoride structure, if you carefully observe, cation and anions, if you compare these two, so anion is smaller in size. Cation is bigger and anion is smaller in size. And in this Ca plus 2 ions, in this kind of solids, so Ca plus 2 ions are going to form FCC lattice. Ca plus 2 ions are going to form FCC lattice, and the fluoride ions occupy all tetrahedral voids. All tetrahedral voids. If you compare with the previous structure like ZNS, in case of ZNS, if you can recollect a zinc blend structure particularly, anion sulfide forms FCC lattice and Zn plus 2 ions occupy 50% of tetrahedral voids. But here, in case of calcium fluoride, if you see, cation is forming the lattice. Which kind of lattice it is forming? FCC lattice. And the fluoride ions occupy all tetrahedral voids. All tetrahedral voids. This is the only information you need to remember, and the remaining things, it may be like total number of ions, effective number of ions, mass of unit cell, Z effective, anything can be calculated very easily. So first let us take the total number of ions in one unit cell. So I hope you know the difference between the total number of ions and effective number of ions. So totally, so that is without any contribution. So without equal sharing, we calculate like that. The total number of ions, calcium plus 2 ions are forming FCC. FCC means the particles are present at face centers and corners. So face centers are 6, corners are 8. So that is equal to 14. And in one unit cell of FCC, there are 8 tetrahedral voids, and all tetrahedral voids are filled. Hence, we can say there are 22 ions in total. One unit cell of CaF2 is having 22 ions in total. So 14 calcium plus 2 ions and 8 fluoride ions. But the most important thing is, in order to find the mass, anything, you should calculate what we call Z effective. Z effective. Effective number of ions, if you take a calcium plus 2 ions are at face centers, and contribution of a face center particle is 1 by 2. They are also at corners. Contribution of corner particle is 1 by 8. And if you calculate Z effective, you are going to get a 4 effectively, even though there are 14 cations in total. But here it is getting only 4 ions effectively. 4 ions effectively. And fluoride ions, they are what do we call in tetrahedral voids. So tetrahedral voids are completely inside. They are not shared by other unit cells. In fact, tetrahedral voids are present on body diagonal, and 2 tetrahedral voids on each body diagonal. So based on that, we can say there are 8 tetrahedral voids, and all tetrahedral voids are filled. And here totally there are 8. Totally there are 8 what do we call anions. But the most important thing is here, by seeing this 4 cations and 8 anions, so totally effectively there are 12 ions, but you should not call 6 ionic pairs. That is wrong. So here one ionic pair means one formula unit you have to take. One ionic pair means you have to take one formula unit. So that is a calcium plus 2 and 2 fluoride ions. So this is one formula unit. This is one formula unit of calcium fluoride. If we say 12 ions, 6 pairs, definitely that is wrong. So we have to say there are 4 formula units are 4 ionic pairs. So here one ionic pair, this is called one ionic pair. Because if you take one calcium plus 2 and one fluoride ion, that is not ionic pair, the stoichiometry is not getting satisfied. So this is one ionic pair, and how many such ionic pairs are present means obviously 4 such ionic pairs are present. And the mass of one unit cell of calcium fluoride, fluorite unit cell if you take, so calcium mass is 40, fluorine mass is 19, but 4 ionic pairs means, so here obviously here that is calcium is 40 and 2 fluorines that is 38. So the formula mass of formula mass of calcium fluoride is 78, and 4 such ionic pairs are present, hence it is 4 times of 78. That is the mass of one unit cell. But if you want to find the mass of 1 mole of unit cells, already in the previous videos also I clarified, I discussed how to convert mass of one unit cell into mass of 1 mole of unit cells. Very simple thing. So this must be multiplied by Avogadro number, because you are finding 1 mole of unit cells. Later the resulting value should be divided with Avogadro number, because you are converting AMU mass into grams. As a result, it is the same, numerical value is the same, but you see it is in AMU and it is in grams. And the number of unit cells present in 1 mole of calcium fluoride. Here, this is mass of 1 unit cell, but here you are finding number of unit cells in 1 mole of calcium fluoride. If you take 1 mole of calcium fluoride, 1 mole of calcium fluoride means undoubtedly we can say that is 78 grams. 78 grams. So that is 4 into 78 grams of calcium fluoride contain 1 mole of unit cells, and 78 grams will contain how many unit cells? If you simplify, you'll be getting, so that is 1 by 4 mole unit cells are present. So in 1 mole of calcium fluoride, 1 mole of calcium fluoride is nothing but 78 grams. And before going to the coordination number we'll talk about coordination number with the help of diagram. And if you calculate the edge length, if you write edge length in terms of cation and anion, so again we are taking body diagonal. So this is a body diagonal, and this is a corner, and this is a tetrahedral void, and a corner is occupied by calcium, tetrahedral void is occupied by fluoride ion. So from the center of the corner particle to center of the tetrahedral void, that distance is 1/4 of body diagonal. 1/4 of body diagonal means that is root 3a by 4, root 3a by 4. And here this distance is radius of cation, and this distance is radius of anion, and 1/4 of body diagonal is equal to sum of radius of anion and radius of cation. And here our requirement is edge length. Send this root 3 and 4 opposite side, and you'll be getting edge length A is equal to, so that is 4 times of RA plus RC by root 3. So this is what do we call edge length in terms of radius of cation and radius of anion. And if you find the packing fraction means the total volume occupied by all ions by volume of unit cell, by volume of unit cell. So here if you see, there are 4 cations, effectively 8 anions, effectively 4 cations and 8 anions. So here totally there are 4 cations means the volume of 4 cations will be 4 into 4 by 3 pi r c cube. 4 into 4 by 3 pi r c cube. But anions are 8. Anions are 8 means the volume of anions will be 8 into 4 by 3 pi r a cube. So volume of cations plus volume of anions you are taking, right? So here 4 into 4 by 3 is common. 4 into 4 by 3 pi is common. So that is rc cube by rc cube plus 2 times of ra cube by, this is how to get this means very clear. So this is what do we call one phase diagonal, and the phase diagonal is occupied by calcium ions. So calcium ions are present at corners, calcium ions are also present at phase centers. In the previous video already I cleared this point for all ideal calculations. So in reality there may be some empty space between these two cations, but for all ideal calculations we are assuming that the cations are in contact. and this total value is phase diagonal. That phase diagonal is equal to root 2a, and that is equal to 4 times of radius of cation. 4 times of radius of cation. Send this root to opposite side. Then volume of unit cell is equal to a cube. Volume of unit cell is equal to a cube. So a cube is equal to 4 RC by root 2 whole cube. And here this is further simplification if you do. So this is the important thing you need to know. So here anion is occupying tetrahedral void. You already know radius of tetrahedral void will be 0.225 times of radius of particle which is forming the lattice. So that will be taken as this ratio can be taken as 0.225, and ultimately if you simplify you will be getting packing fraction is equal to 0.749. Packing fraction is equal to 0.749. So what percentage is occupied means 74.9 percentage is occupied. And here this is about the packing fraction. And if you see, already I told you in reality there may be some gap here. Face center particle may not be in contact with the corner. But for all ideal calculations, we assume that. So in general, FCC lattice face center particle is in contact with the corner. And if you can see, this is what do we call tetrahedral void. So here there are 8 tetrahedral voids here. This is the first one, second one, third one. Backside to this there is one, that is 4, and this is 5, 6, 7. Backside to this there is one more. So this is what do we call the structure. But the coordination number of cation and anion, if you take, see, this is actually fluoride ion. Fluoride ion is occupying tetrahedral void. So this is fluoride ion. Fluoride ion is occupying tetrahedral void. So tetrahedral void is always surrounded by 4 particles. Surrounded by 4 particles, 4 nearest neighbors. What are the 4 nearest neighbors? If you ask, this is the first one. I'm talking about this fluoride ion, this corner particle, this face center particle. So here this top face center particle, and here this face center particle. 3 face center particles and 1 corner particle. So already voids we located in CCP and also HCP. So here these are the voids occupied, and the coordination number of fluoride ion is 4. Undoubtedly that is 4. It is surrounded by 4 cations. And what about coordination number? What about coordination number of cation? So cation is surrounded by, so this cation if you take, it is surrounded by 8 tetrahedral voids from 8 different unit cells. So here this is one tetrahedral void, and it is surrounded by 8 tetrahedral voids, and all tetrahedral voids are filled. Hence coordination number of cation is 8, coordination number of anion is 4. The type of packing is 8:4 type of packing, 8:4. So while writing this type of packing, so first you have to mention the coordination number of cation. Next you have to mention the coordination number of anion. So 8:4 type of packing means, so here calcium plus 2 is surrounded by 8 fluoride ions, and fluoride ion is surrounded by 4 calcium plus 2 ions, and this is about calcium fluoride structure. And the next one is antifluoride structure, exactly reverse. So exactly reverse, only one point is necessary. The remaining parameters will be almost same, but what do we call coordination number of cation and anions are reversed. So if you take Na2O type, this is called antifluoride structure, and in this oxygen, that is oxide ion, will form FCC. Oxide ion is forming FCC lattice, and Na plus ions occupy all tetrahedral voids. Exactly reverse. And if you compare this particular structure with ZNS, if you want, you can compare. In ZNS zinc blend structure particularly, anion forms FCC. Here also anion forms FCC. There cations occupy 50% of tetrahedral voids, but here cations occupy all tetrahedral voids, 100% of tetrahedral voids. If you compare this Na2O with the previous one, CaF2, So here almost the occupancy wise, packing fraction wise, it is the same. But there in CaF2, lattice was formed by calcium plus 2. But here the lattice is formed by what do we call O minus 2. Almost the same thing you will get. You can see here this is 22. Effective number of ions you will be calculating 4. That is again 4 ionic pairs. But the mass is different because one ionic pair is nothing but 2 sodiums and 1 oxide. Two Na plus ions and one oxide together said to be one ionic pair, and the mass of one ionic pair is different because two sodiums is 46 and the oxygen is 16, and almost all same, but the coordination numbers are reversed, and here edge length expression will also be same. But earlier what happened is corner was occupied by calcium plus 2. Now corner is occupied by negative ion, that is O minus 2. So in that way it is different, but ultimately edge length in terms of radius of cation and radius of anion will be same. Packing fraction also you can calculate, you'll be getting the same thing, and the coordination numbers are opposite because the Na plus is present in tetrahedral void. So tetrahedral void is always surrounded by 4 particles, and fluoride ion is forming lattice, and the fluoride ion is surrounded by 8 tetrahedral voids, and all tetrahedral voids are filled. Hence, the coordination number of cation is 4 and the coordination number of anion is 8. And this type of packing is a 4:8 type of packing, because first we have to mention the coordination number of cation, then coordination number of anion. So this is the end of this video, and we have some more structures to discuss, and we'll continue our discussion in the next video. Thank you very much.